let's go. Templates. I like this lecture. I don't love the dynamic polymorphism lecture. That stuff hurts my head a little bit. I saw it hurting your head a little bit. I've had to think about it for a lot of years, so it hurts my head a little less by this point. But this lecture is, I think, a bit more digestible, and also more importantly, it originally, for many, many years, was actually taught quite early in the course. So I think inherently it's actually simpler. The dynamic polymorphism lecture used to be the last lecture of the course, and I think its weight reflects that, whereas this is a little bit simpler. But what in the world is templates intro about? So we talked about dynamic polymorphism. This lecture is about what you might call static polymorphism. We don't really use the words static polymorphism much, or compile time polymorphism. We often use the word templates. Templated classes, templated types. Assignment 3 is going to be templated as well. And understanding how these things work helps us become a better C++ programmer too. Because if you think about it, a standard vector, you know, where you pass in the generic type and enter a double, that's a templated type. You get it, you know how to use it. We're not really showing you how to use it today. We're trying to really unpack all the little nitty-gritty bits so that we can understand everything that's going on. And that includes some of that stuff down there. So firstly, you know, quick recap, polymorphism, provision of a single interface to entities of different types. This probably, this definition would have been helpful in the last one. I guess when we swapped them last minute, it's not really there. But it's a really concise one, which is like, you see, you have a single interface, and we've talked about this, right? You have a dog, and the dog can take in a dog, an animal, a simple interface, and an animal type can take in a dog or a cat or a fish. You know, that's polymorphism. Single interface, different types. When it comes to the static stuff, it comes up in the form of things like this, where you can have a single interface, basically a vector, and that vector can have an int version, a double version, a string version, basically any types of versions you want, and still have that same common interface with the pushback, right? Sorry, I work with like 3 languages these days. Everything melds together sometimes, etc. So we're talking about templates. Now, before we get into most of what this lecture is about, which is class templates, which it's all about classes templates by and large. However, it's worth talking very briefly about function templates, because they're just a small example of how it can work. Now, if you don't have generic programming capabilities in your toolbox, right? If you wanted to create a min function that works for ints and a min function that works for doubles, which is pretty standard, right? Like if you have a min function, you want it to work for ints and doubles. And you don't want it to just like you think, oh, if I just have a min function for doubles or ints or whatever, it should work if things do implicit casting, but that can be a little bit messy sometimes. You ideally don't want things to cast unnecessarily. On the upcasting to double, you couldn't even call that upcasting, you've got like floating point problems. On the double to int, you've got like precision because you're cutting off the decimals and stuff. But this is how you might do it. You might define a min and a min function. One's a double, one's an int. There are rules. This is called function overloading. We touched on it really briefly back in week 1. And there are rules that govern function overloading. Like for 2 functions to overload, they have to have the same name and different parameters. They can have the same or different return types or something like that. But you can't have like an int and an int min and have it overloaded by another int and an int min if they just return different things. So it's all about different parameters. Do you have a question? Okay, sorry, just checking. So this one works because if I call min with that, it calls line 1. If I call min with that, it calls line 4. I've clearly added a hash include to that file. Sorry about that. Didn't notice that comment there. So yeah, you get it. Don't really need to unpack it too much. However, we can use templates with functions, and this is probably the first time you've seen it in code that we've been writing. And it looks like this. It's actually a relatively simple bit of code, because what you do is you take your function and you just write this little piece of text up the top here, which is template type name t, like that. And if you write something that has a template type name t, what will happen is that it is an instruction to say this is a templated function, and there is one generic type that's going to be used here, and it's going to be called t. And then what you do is if you say, previously you had int double double like this, you can just go and replace these 3 ints with a t, like that. Not too bad. Yeah. Now what happens is that when I call min here for both an int and a double, the top one will call min int int, and the bottom one will call min double double. It's similar in languages like Java and stuff like that, because in Java you can make templated types. Where things are different in C++, which is the most relevant part of it, is that in C++, in a language like Java, the templating often happens during runtime, as far as I understand it. What that means is that you just have a single class type like this, and at runtime, it just kind of takes in things. It's nearly like polymorphic at runtime as well. It just takes in different types and figures it out on the fly while the program is running. If we think about C++ principles of lightweight abstractions, what we want to do is create the ability for something to be templated, but we don't really want it to be much slower than this. We don't want to have power, i.e. having to not duplicate, without, with a big cost. So we want it to be quick like this. The way C++ does that is that what we do, and it's quite a little smart, sneaky idea, is that when you template something in C++ like this, what the compiler actually does is it sees this as an instruction, as a template, literally a template of what code to generate in the binary. And what happens is, if I just have a piece of code like this, nothing actually compiles. There is no function that gets compiled here. And that's very different, right, to if I imagine for a second if I have an int min, int a, int b, really quick, return a less than b, a or b, like that. That should compile something, right? So this here actually gets compiled. If I have code if that function will compile into some binary, some machine code, over here, but just this will not compile because this itself is not a function that gets compiled. It is a template for functions that compile, for functions that get compiled. And the way it works is that when the compiler sees someone trying to use that template, it actually goes and generates functions of those types. So if I scroll down here, you'll notice 2 very friendly functions, one here called int min int int, and another one called double min double double. So what's happened here is during compilation, the compiler has seen you try and call a min function with an int, and it has said, oh, we better generate that. And it actually goes and generates that for you anyway. And then it sees us try to use it for a double, and it goes and generates that for us anyway. And if I came down here and tried to do the exact same thing with a char, 2 chars, like an a and a b, it would go and try and generate yet another function, another char there. So in that case, the machine code that has been generated has 3 functions in it. So this is an obvious trade-off, which is that your machine code gets bigger, right? With every possible type that is used, it's going to compile more and more machine code. That binary you run will be bigger. However, the runtime execution of it will be basically indistinguishable from manually function overloading them like that. Right, so that's how it gets around that. It's lightweight abstraction, does it as you'd expect at the cost of a slightly bigger piece of machine code, which generally is not a significant concern most of the time. It's very interesting. So this actually happens all the time. If you have a program somewhere where you've created 2 standard vectors, like a standard vector of ints, I can't remember, like in your assignment 1 you would have done that, right, or something. There's at one point there's a standard vector of strings and then another one of a standard vector of something of strings. I can't remember all the specifics, but if you've done that, then somewhere in the code that's compiled there was actually 2 entirely separate vector types that were defined and then used at runtime. Yeah, and it only happens when you call that function. So the template exists by itself, doesn't do anything. Yeah. That's a great question. Are there any types the function will prevent you from passing in? So the cool thing about that is that you can kind of deduce it because think of it like this. It's no, it won't restrict you outright, like if I had this, for instance, any type in C++ would work there. But as any type tries to shove itself in, it then has to go and compile the rest of the function. And if I pass in a type there, for instance, that doesn't have a defined operator less than, then that type will compile error based on that. So for example, standard vector doesn't have a defined operator less than, as in you can't create two standard vectors and compare, like see which one's less than the other. So if I had this function here and we go back to our little compiler explorer, if I very sillily went and was like, you know what, I'm going to see what a standard vector of ints with 1, 2, 3 in it is compared to a standard vector of ints with 4, 5, 3, 4, 5, that shouldn't compile, pretty sure. What does it? That doesn't compile. I don't think that should compile. I'm not sure I don't know how to work this thing. Because it tries to do that less than, and it's like, I don't know what that is. So it fails there. So it's only restricted by how you use it. Typically by operators is a common one. Yeah.
Why don't other languages handle generics this way as well? So they do things on the fly instead?
Yeah, I don't know why, but I do know a lot of languages will just do it on the fly. I haven't really sat down and really thought deeply about the philosophy, because you'd think, oh, universally, surely a bigger piece of runtime, bigger piece of machine code is like better than slow code, but there might be some implementation efficiencies there. I imagine there's probably an element too with like loosely typed languages where like any language that doesn't know all types at compile time can't do this, you know, because like C and C++, they know every name you see, like, you know, min or a variable name, its type is known at compile time, which means its sizing is known at compile time, etc. Whereas I imagine, I don't know about Java, but if you think about a language like Python or JavaScript, they don't know what types are going to be always at compile time, because, you know, you might have something in JavaScript that says like, you know, const A equals 4, and then you say like const B equals A plus, and then like collect the input from the user. And the user might input a string or a number or something, and then it's like, what's it going to cast that to? I don't know yet. It'll just kind of decide in real time, and then it probably needs something, and it just like spools it up as it goes. So I can explain it for loosely typed things, but for Java, which I think is still a strongly typed language, I don't know why that choice. Someone probably knows. Hope that helps. Well, this is fun. Yep, T is what we call a template type parameter. And this is what we call the template parameter list. There's some definitions for you. I've never really seen someone sit around and be like, the template parameter list, so I wouldn't stress too much. But before we get into templated classes, which again is the meat of this, let's also talk a little bit about type and non-type parameters. This is a funny little thing. I would pay attention to it, but you're not going to see it as commonly as just general type parameters. So it is kind of obscure. It's a very nuanced thing to be throwing at you so early. But here we are creating, because just for a second, you can create a function that takes in two templated types. You could do something like this, type name T and type name U. That's pretty common. If you go to the C++ standard and you look up, what's the type? Is it unordered map? Yep. If you look at unordered map, its definition will be pretty clear and say that, you know, it's templated across a few different things here. 5 things, in fact. We kind of touched on that weeks ago as well. This might make more sense now. So you can have many templated types. However, there's something you can do called a templated non-type. And a templated non-type is where, rather than just saying type name T, where you're saying to the user, hey, you need to give me the type that you want to use for this, we actually give give a type itself, and what the user provides is a value. It's a little bit wacky doodle, but it just means this one's a type that you pass in, this one's a value. If you're not sure what I mean, jump straight down to the bottom of the code here and have a look at how it's invoked. So for instance here, this standard array, which is a templated, sorry. So a bit confusing. Standard array, don't actually worry about this for a second because we're not using it on line 15. So let's just focus on standard array. It is an example of a templated thing that takes in a type parameter and a non-type parameter. You'll see this if you go to standard array. Standard array here takes in some type, and it takes in a size t called n. Now that makes sense because what we know about standard arrays is that they are fixed in size. They can't be, mutated in terms of their size. So we give it a type parameter and a non-type parameter. Now we then create a double one as well. Okay, that makes sense. We kind of get it. We've got an array. You can have an array of doubles and an array of ints, and they can be of different sizes. Sure, kind of get it. What happens then if you would like to create a function that takes in a standard array of stuff? So what I have to do then is I have to say, well, I'm going to create a function called findMin, but what it's going to take in is it's going to take in itself a standard array of type t and of size, and I have to define that as a template as well. Now, this function will work because it takes in that array of size t, of type t of size called a, and then we create a minimum value in it called t, and then we loop through all the elements manually, and then if the next element's less than the biggest one we've seen, we capture it, etc., and then we return the min at the end, which is of type t. So this is a normal function, and if you're overwhelmed for a second by the non-type part, you could really easily condense this down if you wanted to, like this. This would now be a function that only works for arrays of any type that are of size 3. So in this particular case, this code here would compile fine because it works with all arrays of any type with size 3. But if I change this to say 4, for instance, now what's going to happen is that only this code would work because it only deals with arrays of any type of size 4. And similarly, if I wanted to not template it at all, I could get rid of this t, replace all of these with int, and get rid of the template altogether. And now this would, if I change this to 3, this would work as well, right? So this function just works as it is, but only with arrays of type size 3. I can template it. I can template the int onto type t. Cool. Now it works with all types. And then I can also further template that on a non-type here, which is the size. And now it works with arrays of any type and size. This one you don't come across as much. Working with non-type parameters, I'd say, is just generally less frequent. It's mostly you're dealing with templated types. Magic says, what will happen if we type in 2 parameters with a not comparable type? It just won't compile. I mean, in this case, you can't do that because you're comparing the same things of the same type, but we might see a few examples of that after the fact. Yeah. Sorry?
Without the size t. I mean, in the function signature, you just template the holes to the array.
Here?
To t. Can't do that?
Can I just do that?
Yeah.
My brain's melting. I don't know. Let's try it out. Be easier that way. I mean, I guess we don't know the size then. I think that's probably the problem. And then we could look up the size potentially. Can you do a size lookup on a C++ array? Size you can. Yeah, that would probably work if you just did a.size. I think in this particular case it's trying to demonstrate if you actually need to extract those variables out. But also this is actually important because you're going down the right track thinking about trying to make it more efficient. Where this does work is the example I gave before, because you can start to constrain things here and be it's a little bit beyond what we're doing, but you can actually then say, I only want this function to work for arrays of size 10 or less as well. But yes, if you were just a big all or whatever, you could probably condense it down a little bit. I like that you're digging into that, trying to make it work well. Similarly, when you deal with template and type and non-type parameters, you're going to get the exact same thing, which is that it's going to create variations for everything that you need. So if you had arrays of ints of size 3, 4, 5, 6, 7, 8, 9, 10, it's going to create functions in the machine code for all those different things. The idea of this causing our machine code to explode out, that's true. It's like a real thing. Is it a problem? Probably not most of the time. Most of the time these days, if we're writing some C++ code, it's probably not a concern how big the machine code is, right? Like you think about all the biggest things that C++ is used for these days, like deep application software, operating system stuff, all the high frequency trading. Most of the time people just want stuff to be fast. The only applications in which like this code explosion problem I can imagine would be particularly bad is if you are working on like resource constrained systems, like you're doing like Arduino, Raspberry Pi kind of stuff, not like a freaking laptop, and you don't have the space to actually fill it up. Because quite often when we talk about programs, I guess it's like there's like CPU bound stuff and there's like memory bound stuff. Stuff that you run out of CPU before RAM and stuff you run out of RAM before CPU, but there's probably some instances out there, I couldn't tell you one because I just don't know, where someone actually has like a small piece of hardware that has next to no hard drive or memory to load the application up, but it just needs to process a lot of stuff quite quickly. So that would be that particular instance. But in general, like I've never seen someone be like, oh no, templates, they're blowing out my code, I need to do something else. Yeah. Yeah, I think I understand what you're saying. I mean, another way to think about it is like, is it possible to write a piece of code where I actually go standard array ints of size x? Like, might be another way to think about it. And then x here is like, standard size t x. And then we like standard cn into x, something like that, This doesn't work. Trying to think of a good I don't know, screw it, let's try it. No, I don't think it's const. Let me just butcher this piece of code. What do we need? IOStream array, that's it. Let's have some fun. What is that? Oops. Yeah, new laptop, so everything's backwards. Who has a MacBook Air here? It's like this is a MacBook Air. The last one was a MacBook Pro. Still figuring out how I feel about it. Template argument is a non-constant expression. Yeah, probably. Yeah. It's just the compiler being like, I don't know how to do that. I didn't expect it to kind of, yeah, it makes sense. Read of non-const variable x is allowed into a constant expression. Do they say that? Maybe they say that in the size t. They don't really say it's const there. But maybe it's, it's probably in the constructor or something. Implicitly declared. Ugh, C++. Aggregate initialization. See, we could spend years talking about this stuff. Yeah, to be the constructor, no doubt. Because, yeah, I guess the constructor is going to expect a const. I don't know. But, yes, it doesn't work because everything kind of, it would need to know what that is. Like, if it wants this to be const, then this needs to be defined at compile time because you can't change it once it's defined. Oh, not compile time, start a run. You get the point. A vector?
Like you have a vector of size t.
Yes.
And then you call array int on each of those elements within the vector. It's still a variable, but you know the elements vector of like different objects.
Yeah. So that would be like you're saying what if I have a standard vector of, literally, yeah, standard size t, which just contains like this. And then you're like, what if I just create a for loop that's like Should stop calling it stupid stuff. You mean like, why don't I just do something like this?
Or like put none, yeah, inside it.
And then, yeah, I guess you can make that dynamic of some sort. Maybe just make them all 2 for now. I must have screwed a few things up there. Oh yeah, temp vector. Unknown type name num. Sorry, I'm writing JavaScript. This is horrible. Jesus. Non-template argument is not a constant expression. Const null. Is it const auto null? Or const expression.
Isn't that what it said?
Oh yeah. Yeah, sorry. Const expression might work, but it's const expression will just evaluate things. I mean, I kind of get it because you're like, oh, in theory this should work. Non-type parameter argument, non-type template argument is not a constant expression.
If we did this in a constant expression function, would it work?
Probably.
You don't even need a vector, you just make one variable. That makes it simple.
Make it one variable.
Like you don't need a loop anymore, you just have vector equals like for yeah, and then
Yeah.
I think you still need to make the whether vector or null constant expression so that it can compile.
Yeah.
I need a variable name. No,
Thank you.
2 equals.
Ah. Unused variable x. It's happy with that. Was happy with that? Unused, yeah. So it's fine with that. Yeah, I mean, like, obviously, intuitively, I know you can't take an input in. But I've never really had to explain why or the boundaries of that. Because, like, I know this will work, and I know the other one doesn't. But, I mean, if you think about it, if you think about the rules, like the compiler just needs to know the sizes at compile time. It does know the sizes at compile time. But I guess the problem is that it doesn't know the size of the array at compile time, so therefore it doesn't know the type. Because it has to know, like, it has to know this num at compile time, I'm pretty sure. Because, like, that infers the type. Like, without that num, you don't know the actual type of this. So if it can't infer that value at compile time, you can't build the type. That's not a very succinct explanation. It's just intuitive that it doesn't work. I couldn't give you, like, a nice summary of, you know, the particular part of the language compiler that stops that or anything. But that was fun. Thank you for leading me down that. Probably didn't have the time for it, but it doesn't matter. Let's keep going. Well, that's non-type stuff. It's a little bit weird, and we don't actually do a lot of it anyway, but it does come up here and there very lightly. The bulk of what we're talking about, though, is class templates. Vector, array, all those things are class templates. They're not function templates. How would we currently make a stack of multiple types? Like if you've got an int stack and you've got a double stack, right? You could naturally copy them. You could create one called int stack and one called double stack and duplicate all your code, right? And this is much worse with classes than functions, because with functions it's a few lines maybe, whereas classes you've got to copy all of the class methods and all of their associated implementations. You know, think assignment 2. Imagine doing assignment 2 for like different kind of filter views, you know, it would just be kind of crazy. So we want a way to be able to template that. So I've got here, I've broken this up into a few things. This is a templated class. Now, thankfully, it follows very similar principles to what we've been talking about so far, which is that you put a template type named T at the top, in the case where there's only one templated type. And then any instance you have of int or double, for the int and double stack, you just replace with T. So, you know, you've got push T, top and const top t. I think they're the two main instances of it. Oh, and then standard vector t. Right, so that's pretty easy so far. Yeah, okay. Oh yeah, and then implementation. So then we've got this here. When you define, and you'd be familiar with this from assignment 2, when you implement those functions, when you give the definitions of it, you need to put the template type name at the top as well. I want you to think of the template type name keyword as a little bit like namespacing stuff. Like if you're outside of the class, you need to explicitly namespace the things again and also template them again, like this here. Right, so just like you need the stack part here, if a namespace stack push, you also need the template type name t. Has anyone noticed anything funny about these two pieces of code? It's all right, we'll come back to what's funny about it. If we were to call our stack, you could do similarly. You could create a stack of ints, copy it, yeah, like, naturally, then a stack of strings. Like, I don't need to kind of show you the same kind of stuff over and over again, but we could create different types. Create stack of strings, stack of ints, stack of doubles. And to your question earlier about, like, would it just work for any type? It really depends, again, on how it's defined, because if we have a look at this here, it's just using an underlying vector. It's just calling vector functions, so there's no problems there. And if we look here, we're just iterating through it as well. And we're just iterating through the vector. So something like this would probably work for any type that could be printable, I guess, because like if it doesn't have some kind of operator output, then it won't compile. But yeah, besides that, it'll work for every type. So lots of fun. And yeah, we're just talking here about, this is the default rule of 5 for templated types. Like if you don't define one of the copy or move, assignment or constructor or the destructor, it will go and create these. This is what you would write for you to create them yourselves, which looks exactly like what you've seen before. It's just that there's template type name t above everything there. So again, fairly straightforward stuff. One area that templates get a little weird in, which I kind of made a light inference to before, is let's imagine for a second that I have these 3 pieces of code. Let me put the main one at the bottom. So I've got my main function here that just tries to min 1, 2. It doesn't hash include something. Oh, yeah. It should probably hash include it still. Should probably hash include inc com min.h, because otherwise it won't know what to compile, right? So when we see 3 files like this, okay, we've got our main, it calls min1, 2. We include the .h file, right? So that it can compile it together. And then we have to link the implementation file later. This has nothing to do with classes. This is just like a really simple function example. This is basic C, C++ style stuff. It's trying to slap it all together. Now remember, compilation and linking are 2 separate steps. So this file here compiles with this file here first, and then this file up here compiles, and then they get linked together. Because this one can compile and not know how min is implemented. All it knows at this stage is that min takes into things and it returns a thing. It doesn't actually know how it does it, just the higher level kind of API of it. Then it links that up later. That's how you would typically do stuff, and you could try and compile those things together here. And let's try and do it ourselves. If we just go straight into the folder, see what happens. I don't know if I have Clang installed, actually. I do. That's good. No such file. Oh, right, because yeah, they're just different file names. What is it? Inc com min.cpp inc com main.cpp -o main. This is not going to go well. Use of undeclined. So this is where things get really interesting, because this piece of code here, if I can maybe change it up for a second. If I get rid of the templates and I replace this with an int, and I get rid of that template and I replace this with an int. Actually, that should have been a t. Never noticed that. So in theory, this code should compile. What have I not included here? Did you mean fmin? Did I not save it? What's the problem? Okay, so that one compiles, right? We get that. That's like 2521 or some other equivalent course. However, once I add the templates in, template type name t, template type name t, t, t. This is the error we should have been getting before. Undefined symbols, int min min reference from main, but can't be found. So what is going wrong here? Any ideas of explanations? So this is an example. You don't really see this a lot, but this is an example of code that compiled successfully, but didn't link successfully. What happened here was that this piece of code here basically compiled. Well, I mean, simplified it. But the way I want you to imagine this is that when this particular file here tried to compile, what do we know about templates? What did it compile to? Nothing, right? Because there's no invoking of it, right? So because you got to remember, the two CPP files are compiled separately. When that one got compiled, it got compiled to nothing. So then we tried to link the implementation, the definition, to its usage over in the main function, and it was trying to link it, and there was nothing to link. So what ended up happening there was that it was like, I can't find anything because nothing was instantiated. And then you're like, oh, well, now we have a problem, because it all makes sense when you put your main function in the file with the definition, right? Because they're all together and they can compile together. But it breaks down in this particular example. So the way around that, I've made some allusions to this, is that when we define templates, we actually have to define all of the definitions in the .h file. It's a little bit backwards, because if you go back to what we talked about weeks ago, we said that you keep stuff out of the .h file, right? Because what happens when you hash include a .h file? It copies and pastes all the source code into that file that's hash including it. So if I take my template definition and I put it in the .h file here, right? This will now work fine if I try and run it. I don't even need to compile it with the other CPP file. This works fine now because how it actually functions is this whole piece of code here just gets copied and pasted in like that. That's compilation. That's all hash includes are. They're not really that much more complicated. So I need to put those definitions in there. Now, the reason we said not to put stuff in the .h file for assignment 2 beyond trivial things is because it bloats up the size of, the compilation, because it's got to, like, imagine that this .h file in the middle is like 10,000 lines of code. It like just copying and pasting it into maybe hundreds of pieces of code. It's just like bad practice, However, when it comes to class templates, you just have to. It's just like how it works. So we do always have to put the definitions in the .h file. Now, if you go back to this piece of code, it was pretty easy to miss it. It was pretty easy to miss what we were doing, but if we have a look at our class template, these two here, what you'll notice is that even though we broke these up into two files, how that worked, and I think I've kind of done this back to front here, you'll see this kind of a certain way, is I've got this file here called templates start2. What you'll see people do might actually go and hash include inside, imagine this is a .h file. Let me just rename these so it's a little bit more digestible. Imagine I've got my stack.h file. What you actually do is, rather than putting your CPP file over here separately and they get compiled separately, you actually can hash include your definitions straight into the .h file. You don't have to do that. You could also just copy and paste them straight in, like this. That's fine too. They just have to be in the .h file. They have to be in that thing that's directly included by who's using it. And yes, for simple ones like this, you could go define them inside the class itself, But in general, we still try and keep the class nice and tight and succinct. It's just that the definitions need to be literally in the .h file or hash included from the .h file to a CPP file, which is a bit weird because you don't normally do that, right? Like you normally will go and hash include a .h file from a CPP file. But I mean, for things we're writing in this course, writing one big file is fine. I would just do that. But they all need to be in that .h file. Oh yeah, this is just like an academic comment. Here it's basically saying that C++ will sometimes only actually instantiate members that are called. So what they're saying is like, in this particular function here, int.com stack, because you create a stack class of type int and then you call s.push, the compiler will often, for optimization reasons, not actually create the pop function. It won't put it in the machine code because it sees that it's not used. And I think this is just because, like, when you write a function literally, it's going to put it in the machine code because you wrote it. Sort of. This is where things get tricky with C++ because they say things like that. But if you put the optimizer flag on, C++ sometimes won't compile anything. Like if you make a program like this, int main, int I equals 1, I plus equals 2. It's a cute program, very productive. If you just compile that as is, the compiler will produce machine code. But I'm pretty sure if you turn on certain optimization flags like -0 or -03 or something like that, I don't know the specific one, sometimes it will actually produce nothing as the binary or some equivalent to that, you know? So this is why like these general rules get really tricky. The other ones we used to mention in the course a lot, I probably said this before, that if you don't mark things as const, the compiler can't do optimizations because if there's const memory, it can reshuffle it. A lot of compilers now, from what I've been told, will actually see things you don't use and mark it as const for you in certain conditions too, which is why I get worried about being heavy-handed with some of the like, this is what happens, because no one, honestly, I feel like knows what happens half the time with what compilers are doing. But that's just a general comment there. Now, static members. This is kind of now just kind of unpacking the, back in week 3 we talked about things like static and friends and all that kind of stuff. This is what goes on when it comes to those various things in the world of templates. So when it comes to static members, each template instantiation has its own set of static members. This is a funny one to think about because what I want you to imagine here, because we've got this class called stack and we've gone and created a static member called numStacks. It's like a reference count, you know? We've got a reference count of stacks. We haven't really done much with static in this course, but if I want to go and define I don't think we use it anywhere here. Yeah, I don't think we actually implement it. But this static element here, the number of these that are created is based on the number of instantiations of stack. And what I mean by that is, if you think for a second that you create a stack of type int A, and then a stack of type int B, and then a stack of type double A, and then C, and then a stack of type double D, each stack, so there's a stack int static, and then a stack double static variable, if that makes sense. So like there are 4 objects here based off how many types? 2 types. You have as many static properties as there are types, because remember, static properties or methods are associated with the type, not the instantiation of the type into an object. That is probably going to have 0 relevance on your actual life, but it's a fun fact to understand how static works. Because obviously when you have a non-templated class, there's just one static variable, right? It's like why it's static. It's just to do with the class once, but templates is as many times as there was an instantiation of that template. Yeah.
The static variable is not of like type 2 or why would that be? Like if it's always going to be one type.
I don't understand what you mean, sorry.
So like in this example, it's a static int, right?
Yes.
It's not t. So why would we have multiple different for each?
Because each stack of a type T needs a count of the number of stacks of that type.
Yeah, but what is there any way of getting around that? Like say if you want all your different types to like class instantiations have the same to share like static members.
No. Yeah. I mean, this is the thing. Templates are just a form of metaprogramming that produces the equivalent of having written two separate stacks at the end of the day. And I mean, this piece of code is interesting. I don't think I butchered it yet. I can probably run it. Why is there no build folder? Oh, it's back. None of you help me anymore. Static. Cool. So if I run static, like this, you'll see that I get a 1 and a 3, which actually makes sense because what I've done here is I've gone and created 1 stack of floats and 3 stacks of ints. And then I've tried to print out the public, count of those if I want to. So that's just how that particular one works. Friends, each stack instantiation has 1 unique instantiation of a friend too. That also makes sense. This is not really anything particularly new because, like, if you think about it, each instantiation of a templated type will also have just 1 method for that type too. Basically what we're saying here is friends are like normal functions. Because if I create a stack of ints, I'm going to have a push function for the stack of ints. I'm going to have a pop function for the stack of ints. I'm going to have a friend operator less than for the stack of ints. It's kind of a, if I didn't say anything, you'd probably just infer that. But that's more just for completeness. Default members. So we can provide default arguments to templated types where the defaults themselves are types. This stuff gets a little bit heady, I think. This is where is it? Things start to get weird. So here, what I have is I have a stack of type T. However, I've also got this thing here called cont, which is the container that I would like to store the stack T in. Maybe I want it to be stored in a vector. Maybe I want it to be stored in a DQ. Maybe I want it to be stored in a queue. I don't really know. And what I can do is I can actually pass that in here. Now, this particular example, I have mixed feelings about because it demonstrates something really obscure, really interestingly. But if I could start with the default members, what we're actually saying in a nutshell is that if you have a type, maybe let me grab the stack like this, what you can say is that, trying to think of what a good example is. Maybe in every stack you want to store a secret, and that secret's going to be of type U. So you have a type U here like this. And when someone goes and instantiates you, what they are going to do, like this, is they are going to create a stack of floats with a type double or something like this, or a standard string to store the secret in, and then maybe, for real completeness, imagine we have a function that's like set secret, U secret. It sets secret to be secret. It's a void function, like something like that. And then we say like fs.setSecret. We pass in, I don't know, pancake. Pandan? Does anyone like Pandan? Okay, we'll just keep it as a boring pancake. Right, so this piece of code is just taking in a second type. And if we wanted to change this to a string, we could change the secret from pancake to like 654. Cool. What we're saying is that you could do a default argument for templates and say, by default, just make U a string. So that if no one actually specifies it, it's just like a string. That's all we're saying. That's the point. It's just this part up here saying that you can treat types just like you can variables, and you create a template, a default, where if someone doesn't explicitly define that when they are, defining the type, then it just defaults to that. This particular example, which is really trying to absolutely cook your brain, is trying to show you that you could create a template of type T, but you could then also change the container that's included within it. So you could come down here and say, I don't actually want the stack to be use a vector of ints to store it. I'd actually like it to use a standard DQ of ints to store it. Right? Now, this is a completely useless piece of code broadly because that's really weird. And also, it's not going to work with much, right? Because how the compiler will take it in is it will take in that type and then it will try and perform all the operations on it that we don't have defined here, like pushback and top and all that kind of stuff. So if it doesn't have all the same capabilities that you were relying on vector for, it won't compile. So an array won't work, a queue won't work, a dequeue. Sorry, wait, am I getting this mixed up? It's like list and forward list. I think I mean a list will work because a list can do pop and push, I think. Could look up the library. But the point is that's how we can do some default arguments there. This is where things get a little bit more interesting. I'm just having a quick glance. Yeah, so now we're going to talk about specialization. So the templates we've defined so far are completely generic. That means we define them once, and then we just use that template for everything. But there are two ways that we can actually redefine our template a second time to create a more specific use case. So that means that we define a stack, and then we kind of copy and paste the code over here and do something different with it. The first one is what we call partial specialization. The second one is what we call explicit specialization. Partial specialization is when we define the template for another form of the template with the same type T. That one I don't see a lot of, but a really common case might be if you have a template, right, that works on a type T, but then you also need it to work for a type T pointer. So what you do is you go and, define a second one that says this now works with a pointer to a T instead. That one I think is a little bit heady. The other one is explicit specialization, where you describe the template for a specific type. Basically, you create like an edge case for it. So you say, like, this is how I want a stack to work for everything. However, if someone tries to create a stack of strings, I'd actually like you to have a different implementation. Now, again, I know when I say those things, you're like, okay, I kind of get it, but why would you do that? It's kind of the question that it begs itself. When to specialize, you need to preserve existing semantics for something that would otherwise not work. Now, again, the funny thing about this one is a lot of the benefit of specialization actually pays itself off when it comes to metaprogramming, which we talk about next week with type traits and type transformations. So I'm probably not going to go into a huge amount of depth with it now, just because the examples will be better. Because things like isPointer and isIntegral are kind of tied to the type transformations and type traits next week. However, an example of one that I always found interesting to read about is that there's actually an explicit specialization for standard vector based on bools. Now, just to give you a sense of the code for a second, that peep door just goes crazy. If I create like a templated class here, it's going to, maybe imagine we're defining vector together. Namespace std, cute, templated type. My class is called vector. Great. What's it going to do? Well, it's going to have all the standard stuff like, push back, which is going to take in a const t reference to t. You get the point, right? We define the vector. If someone says, you know what, I actually want to have let's get rid of the std, it's not confusing. If I want to create one where for Booleans specifically, I want to do something different. What they do is they copy and paste the entire piece of code. They get rid of the template type name t, I think. No, they just leave, I think it's just they leave that. We'll see the code in a sec. And then what they do is they replace the int with the specific type. The t, sorry. So they get rid of all the t's in the explicit specialization. They just replace it with the specific type they're trying to explicitly specialize for. Now, in the case of standard vector, I haven't read the doc in it in a while, but there's basically an explicit specialization for bool where they've tried to be really efficient about it. Because if all your vector can do is store trues and falses, right, which are just a bit in memory, and what they, I think, do is they actually, like, because you know how like an int is like 8 bytes, or like, what is it? The smallest piece of data you can have is a char, right? Which is 1 byte. But a char has how many bits in it? Like 8, right? So what they do is they basically make a standard vector of chars, but each char they use to store 8 bools inside of it, right? I haven't seen the code of how they implement it, but that's my understanding from what I've read. Which makes sense because they're like, you know what, there's actually just like, this is the code of how a vector works, you know, pushes stuff back and stores this and smart pointer that. However, if someone wants a literal 1-bit data type, well, we can create the illusion that they're treating it like real memory, but we'll actually go and like break it down even further. And they probably had to do a few funny things with it, like, because a byte is the smallest addressable amount of memory on a computer, you know? So you can't really get a specific address to anyway, you get the point. But yeah, so that's a good example of explicit specialization, because just because you create a generic type, you don't want it to be that forever. Sometimes you're like, this is a good use case of it. So if we just lean on that example I described there for now, when are times that you shouldn't specialize? You should never specialize functions in general. There's no real need to. That's why we have function overloading. You know, like you can literally, there's no point creating like you can just go and define the function that's different. You know, like function overloading exists in the language. And you also shouldn't do it if it's not obvious. There's a general, you know, principle when it comes to a lot of programming, which is like, if something's not obvious, try not to do it. And what that means is like, you know, when someone goes and does this, they create like a standard vector of bools, and they use some funky way of storing it. You're not really going to like, it's not going to confuse you. It's not going to break your expectations. You're still going to push to it, pop from it. Suddenly it'll just use less memory, you know? But you wouldn't go and explicitly specialize, you know, a vector of standard strings and suddenly it's got all these extra functions and does all this random stuff. That would just be weird, right? So if you want to add, you know, capabilities, you don't do that just by specializing. You'll typically create kind of separate functions for that. So we're going to play around with this stack template. This is how we're going to look at these couple of specialization examples. This is it. The declarations and definitions are defined in here. We have our stack, top, push, pop, size. This is a pretty silly class, right? Because it's just using a vector, kind of benignly, but it helps kind of paint the example. That's why we use it. So, you know, push, back, pop, whatever. It's just a light abstraction for a vector. We've got a sum here, which is a nice little throwback to our STL algorithm, standard accumulate, stack begin, stack end, where stack is just the vector here. Maybe just for simplicity, I'll call that vector. That might read a little bit better for all of you there. And then I've got my CPP file where I create a stack of ints and I push 6771 and 1917 to the stack, and then I check out its size, top, and sum. And you know, because it's a generic type, C++ will create an int stack for me automatically. So if I go and run make stack main, cute, stack main, there we go. I print out the size, which is 2. I print out the top, which is 1917, because that's the last thing added to it. And then I print out the sum, which is those two numbers added together. Works fine. We've established that the code works. Let's look at partial specialization now. I don't love this example, so I don't want you to dwell on it too hard. But in this case, we're going to partially specialize for pointer types. There is a class here called stack partial, which looks really similar. And then I have one here called stack partial main. You'll see the only difference between the stack main and the stack partial main. I don't know why they didn't need to include IOStream. That's weird. You'll notice the only besides, oh my god, sorry all. That's not very good of us to have that so inconsistent. This is the only difference between, there's not much difference between the two pieces of code, right? Like on one of them we are, you know, a stack of int stars and one's just a stack of ints, and the one with the int star we have to pass an address to the ints into it, right? Because it's got to store an address to those particular pointers. So you'll see the stack main one works fine, and then also the stack main partial. What did I call that in the CPP list? Thought I did that. Oh, whoops. Yep, so that one works as well. Now, if we have a look at the implementations for a second and we try and dissect those, also you'll notice so there's those two. What you'll notice is that not a huge amount is different here, but one kind of key thing is different, which is that how we accumulate stuff is different. So my stack.h simply accumulates it by just saying, can you just go through it and sum it up? Just like accumulate it normally. Just use the operator plus. Whereas my stack partial, because we're passing in a pointer, obviously if you're storing a stack of pointers and you sum it up, you're not trying to add all the memory addresses of the pointers together, right? That would be the default behavior of just keeping our normal stack here, right? And what I mean is, like, if we've just got a normal stack that doesn't deal with pointers, and then I try and say, you know what, I'm just going to get you to deal with pointers now, you will see that it will crap a brick when I try and do that, because it'll try and see the incompatible pointer to integer conversion. So somewhere there, this is deep inside the accumulate library, it's going to be trying to add pointers together, right, as it accumulates stuff. And that's where it's getting confused. However, if I simply use our stack partial implementation, this will now work because our stack partial passes in to the accumulate function a lambda. And our lambda here is simply telling us to, hey, you're going to be accumulating an int. Should probably be type T, sorry. TA, not, wait, what? No. Oh, sum always returns it in. Wait, does that make sense? I guess so. Yeah. Maybe that should be T. I don't know. I've never seen that, never thought about that deeply. It doesn't really matter. Let's just assume it's always summing up numbers for now. Then it's going to add up the A, the running total int, with the dereference of the pointer. Now, the reason we call this partial specialization is because we have given a specialization of our original templated type. However, we still haven't made concrete T itself. It's still templated. This is still a generic type that can take in any T. We've just done a pointer version of it. So the definition of a partial specialization is when you have your normal template, you create another template that specializes, but it still has a templated type. Whereas an explicit specialization, which we'll look at here, will actually drop the templated thing altogether, right? Because this is another example to do with isVoid, which we do talk more about next week, where this is the templated class here, and this is the explicit specialization, no reference of T. So if there's still a reference of T in your specialization, it's a partial one. If there's no reference of T, it's explicit. I really hate speaking in this course. There's just so many words. Such a wordy thing to talk about. Quick teaser for next week. This is an example of a type trait. It's actually really smart how they do it in C++. So you can, for instance, do this thing where you say, hey, can you check if you basically, what this is doing is it's basically creating an object. It's not even creating it's not creating an object, sorry. When you do this, the compiler goes, oh, you want a class, a templated class called isVoid of type int, right? And that class is going to have a static field called val, which is false. And so that static field is always false. However, what they do is they explicitly specialize a version of that class only for voids here, right? So see how, well, it doesn't really say T there, but it's saying this one's for voids. And if it's a void case, then it's true. So it's a really wacky thing, and we talk about it more next week. But this is a really common use of explicit specialization because it allows us to do these kind of, these are compile time checks, basically. Right? Like we're familiar with runtime checks. In different languages you've got type of, or in Python or whatever, then there's like instance of and stuff like that. They're all runtime checks. This is like a funny C++ way of doing like a compile time conditional. So like this actually turns into a value here. Anyway, let's talk about it next week because it's far more depth and is deserving of 60 seconds. But that's another case of explicit specialization. The other one I gave was the standard vector Boolean example, though I don't have the code for you to show you, but you could imagine that it's going to be doing some funky stuff with bit shifting and all that other stuff that gives me PTSD a little bit. Oh wait, are we doing this today? I think I decided to move this forward now that I remember it. Yep, okay, I did, because I was like, yeah, I think this was it. I was like, well, if explicit specialization is mostly to do with type traits, why don't we just talk about type traits today? So you've seen numeric limits before, right? I think it comes up in a few pieces of code. I think it came up in assignment 2, right, as an example? Something? Yeah. So if you ever thought about how does numeric limits work, it actually uses explicit specialization quite heavily. Because what it will do, you just maybe pull up the code, is it will define, it'll basically create a, there'll be a template like this, and they'll say there's a min function somewhere, a static min function associated with the class type. And then what they'll do is for each type that has a numeric limit, like an int or a double, they will go and basically define it explicitly as an explicit specialization like this, so that when you invoke it, what actually happens again here is that the compiler says, okay, standard numeric limits, that's a templated type, so we're going to go instantiate it, but a double, is there an explicit version of it? There is. So now in the machine code, I'm going to go and create this particular function. So somewhere in the machine code that gets created, which makes sense, a numeric limits of type double. And then when this part of the main function goes to invoke it, it just invokes that particular class here. It doesn't create an object because there is no object created. It's simply calling a static function of that class type, which returns a value of whatever else. And that's how we get, again, a great little piece of code that at runtime basically has very little overhead, and it knows exactly what to call at runtime. So you as a programmer can kind of have this nice program where you're like, yeah, numeric limits are double or int or float or something like that. But at runtime, it knows exactly what function to call. And in fact, the compiler sometimes will note during compile time that you are calling a function that has a non-parametered return, right? This function returns the same thing every time you call it. So there's nothing that would theoretically stop the compiler from actually injecting that value straight into a function, into the machine code. So there's no even function call that has to happen when the code runs. What I mean by that is, like, if you have it, nothing stops the compiler here seeing that, like, there's this and just being like, well, you know what does that evaluate to? Well, it evaluates to, like, God knows, let me just pretend it's that. It'll just go and be like, well, might as well paste that there, and you know what, we'll just go and paste this here, and then it gets rid of all that, and it's like, yep, there's my program. The compiler can do quite a lot if it can see everything at compile time, because there's no dynamism there. Nothing's going to change. I'm not saying it'll do that again, but nothing stops it doing that, which is really interesting. And this also works really well because this particular library, numeric limits, you know what? It'll be defined differently on different machines. Because if you're running a 32-bit machine, you're going to be installing a particular version of C++ and its libraries. And if you have a 64-bit machine, you'll be installing that version. And on both of those versions, they simply define that differently. So those values will be different on different kind of hardware, because you do have different numeric limits on hardware. And that's how we can write C++ code to be super versatile, because if you write C++ code that uses the numeric limits, you're basically just relying on the fact that someone else has gone and implemented that differently for different machines. So now you don't have to worry about what the limit or whatever is. Someone else deals with it. That's great. We call these things type traits. There's a lot of them. Well, there's different libraries, but there's one library called limits, which that is for. Type traits are used to characterize a type. They basically reduce, I always think of them like, you give them a type and you can infer an aspect about them to a value that you can reason with. You can put this in an if statement, you can put this in a for loop. And that's what makes them so useful. Type traits are useful if we go back to our first example when we had the type and the non-type. Do you remember how we were like, what's the largest value? Well, you can use them with templates too. You don't need to actually know what they are to use them. So if you're writing a max function to find the maximum, actually this one's slightly different. Well, what you can do is you can set the largest value to be the minimum possible of type T. I don't even need to know what type T is. These things kind of bootstrap on top of each other really well, so that when someone comes down here and creates an array of ints, well, what happens is this function gets instantiated, and whilst it's creating it, it goes and creates a numeric limits of type T, which has a min function which has a particular value, right? So these things layer on top really well. In fact, a lot of type traits aren't often used either with, like you would rarely use them explicitly like this as much as they're used in templated types all the time. There's the isVoid function and the isPointer one. These are the same things. This is kind of probably one of our last examples of, like, on the left here is explicit specialization, and on the right is partial specialization. So both of these are type traits because they help us infer something more about a type. But because this one still has a type name T, it is partial. And you can see there that this one is used to figure out if a type is a pointer. So that's pretty cool. Like, you can basically give something into this like is pointery weird thing and it will tell you what it is. That makes sense? Is anyone lost? Anyone got a question? Kind of just moving like a bulldozer at the moment. I don't think it's too hard. Trying to imagine how you'd use this is hard because you're like not too sure, but all right. Speaking of how we'd use it, here's a great example. So I have a, I call this a great example. This is an example. I create an int, I create a long, I create a double. I want to write a function that I can pass in that I, int long or double to, and it will print out whether it is a number or not a number. And what's cool about this is I can go and create a templated function that'll take in any type, right? However, what I can do is I can condition how it works based on, various type traits. So the type T, I want to know traits of that type. For instance, I can say, you know what? If type T is an integer or type T is a floating point type, then I'm going to print to the terminal, that value as a number. And if it's not of type int or type double float, then I'm going to print that it's not a number. And then I can call it on number, string, string, and you'll see what happens is that it prints out that really nicely, Again, I've got a really elegant way here of having this actually work with my code, and I don't know how successful this will be because I've never tried to paste it in here. But you'll be able to see, again, a lot of this. You'll see that we created a test if number type for ints. We created a test if number type for longs, for doubles, for char const stars, because remember that string, these are both string literals, which means they both use the same one. But it hasn't got anything about the... it has gone and created a char traits. Yeah. It's clearly using the type traits. I imagine that, I don't actually know how to read this one. That's probably why I wasn't going to talk about it. It's interesting that I don't know what char traits is. I was kind of expecting that to be calling like, one of the is integrals or something. But obviously this compiler is going to hide a lot of code that's imported in libraries. It's not going to include all of the standards, cout stuff, because they'd be big chunks of code. So a lot of the code we've imported there that's getting instantiated would just be kind of hidden away from us there. But that's an example of how you can use type traits to make your code more dynamic based on types. And if we were to do things the other way, we would show you what type traits are, and you go, oh, wow, that's really cool. And then we'd be like, well, how the hell do these actually work? And then we would have done the first hour of the lecture, right? So we've kind of gone the other way to some extent. But that's specific to specialization. I don't really want to talk about this one. I kind of debated whether I wanted to leave it in the course this time, because it's just so really nuanced and specific, and I don't think a lot of people digest it well, and we don't even do anything with it. It's super academic. So you can go kind of read up on it in your own time if you want. But basically what we're saying is that if you create a stack remember that earlier example where we had a stack of ints and we said we want the data structure that it's stored in to be a standard vector of ints too? There's basically, if you write a lot of very confusing code, you can reduce that code down to saying a stack of ints using standard vector. You don't have to specify that it's an int as well. Makes your code a little bit cleaner because you only have to define it at one point. And it involves a lot of things like this, which get very confusing, like saying, I've got a template type name T, template type name container. And again, I've done this enough times to talk about this for 20 minutes. And everyone kind of gets it, but again, what's the point? You're just not going to be doing that. It's like a really obscure thing. But if that fascinates you for some reason, go read up on this, and I can link you to my 2021 lectures, and you can check it out there. But I don't really want to spend time on that today because we've got a few last things to talk about. Template argument deduction, kind of wrapping up. We've got, that is actually it. Wow. So template argument deduction is the process of determining the types of type parameters and the values of non-type parameters from the types of function arguments. So basically, we've talked earlier about type and non-type parameters, but we haven't talked about how they're deduced. So if I've got my find min function here, in this case, it's relying on a... Oh, that's so ugly. Why is that written like that? This one's doing what the other one was doing, except instead of working on an STL array, this one's just working on a C-style array. That's what that syntax is, like a C-style array of size, and we're kind of doing the C-style array syntax with it. But the point is, well, there should be okay. So with non-type parameters, as in the value parameters, if you will, implicit conversions behave just like normal type conversions. So what we mean by that is that, how would I best explain that one? It's basically saying if you have a function that takes in, say, doubles, you can try and pass in an int to it, and it'll take it in because there's normal type conversions there. Type parameters, I don't know. It's a little bit, I don't think that's the best example for it either. There's not even really a lot to talk about there. Yeah. Again, I probably don't even think this one's super relevant either. The tail end of these two things, once again, come from the fact that this course was originally a compiler course. So if you think about the topic of template argument deduction, that's literally a topic taken straight out of Compilers 101. It's like you program a compiler to figure out what the templated types are there. And I just don't think the rules really add that much value to the knowledge you're trying to achieve in this course. So I'm probably not going to spend much time trying to vaguely unpack what that is either. So don't worry too much about template argument deduction or template parameters. There's just no real meaningful relevance to those at all. But everything else we've talked about is super important. And again, just to really quickly summarize it for you, because it's getting to the complicated end of term, we spent a while basically talking about, we were like, you can template functions, easy. Then you can template classes, not too much more complicated. However, the caveat was when you template classes, all the definitions have to be in the .h file. That's the big kind of gotcha for templated classes. Then we kind of covered how static and friends behave pretty intuitively. And then there was a big piece on specialization where we said, there are times where you need your template to behave in certain ways for specific types. And we can do that either by specializing, half specializing, where there's still kind of a templated aspect to it, or we can do that by fully specializing where there's a very explicit aspect to it. And the partial specialization examples are mostly around things like pointers. That's the most common case I've seen, and the explicit specialization is used most commonly in type traits and type transformations, because things like is pointer, is number type, is void. We'll see ones next week where you can convert types from one to another. That's where they're really heavily used for. So yeah, I'll probably cut these two out of the slides anyway, so you'll see them disappear. Any questions before we finish up today? Thank you.